I want you to imagine I have two masses and I've connected them with a string. I'm going to take that string and drape it over a pulley. Now at this point in time, our pulleys are going to be massless, frictionless pulleys. I know that's totally just bogus, but the reason why we need to do that right now is because we're not at a point to analyze rotational motion, making the pulley rotate. So by the pulley being massless and frictionless, I mean the string is just sliding around the pulley without the pulley doing anything. It's just a placeholder, just holding the string in place, that's it. So our pulley anchored to the ground, our two masses, we'll use the 5 and 12 again. So the 5 kilograms starting out high, 12 kilograms starting out low, which would really not help us much, I suppose. Let's make it a little different here. Let's put the 5 low and the 12 high. Sorry for messing up your picture. That way we have more room to work with is the 12 falls. Hopefully it's fairly obvious that with the 12 kilogram object being heavier, it's going to be able to pull the 5 kilogram object up. Since they're attached by a string or a rope, whatever needs to be connecting them, it's not a bungee cord or a spring. It's something rigid that's going to maintain its length between the two. So as the 12 kilogram falls, the 5 kilogram will rise. You got that? What can you tell me, if we call this mass 1 again, what can you tell me about the acceleration of mass 1 versus the acceleration of mass 2? Same magnitude, but opposite direction. So A1 will equal negative A2, or A2 will equal negative A1, whichever.
So the rope is infinitely stiff as well then?
Yes. So A2 is equal to negative A1. They're going to have the same magnitude because they're attached to a rope that's not going to stretch, it's not going to break, it's not going to get shorter. So their accelerations will be the same. Now it's a little harder in a case like this to treat this as one object as a whole and just treat it as one object of m1 plus m2 and find the acceleration that way because they're not moving along the same line. So it's usually easier to go ahead and let's look at both objects separately, but then we can combine their equations. For example, mass 1. What forces are acting on mass 1? There's tension and the force of gravity. Exactly right. There's tension from the string or rope that's connected to it, and there's a force of gravity because we can't turn gravity off, so there's always going to be some gravity there. What about the 12 kilogram? It will have a force of tension because it's connected to a rope that's pulling on it, and it will have a force of gravity. Exactly right. Now, by treating our pulleys as massless, frictionless pulleys, we're ignoring any rotation that the pulley will have. So we're just assuming the rope slides over the top of the pulley without making it turn. That makes the force of tension on this left-hand side equal to the force of tension on the right-hand side. So these force of tensions will have the same magnitude. They'll be our opposite direction. Well, actually, they're both up. So they have the same magnitude, they're both in the positive y direction. When we actually look at rotating pulleys with mass, natural rotation, that won't be the case. The tension won't be the same. because it wouldn't be able to make the pulley rotate if the tensions were the same. But for now, pulleys are massless, frictionless. They're not rotating. So for mass 1, conveniently on this problem, we only have the y direction to work with. There's no horizontal forces acting on these. So for mass 1, we have the force of tension upwards. We have the force of gravity downwards, so we need to subtract. Now, force of gravity depends upon mass and acceleration of gravity, mg. So I'm going to put that in. So m1g. Those are the net forces acting on our mass 1, our 5 kilogram object. So that has to equal mass 1 times its acceleration. So m1a1. Net force, so looking at all the forces acting on our object, adding them all up in the y direction, has to equal the mass times the acceleration in the y direction. Are we okay getting that equation? Well, conveniently, the equation for mass 2 will look similar. The difference is we have m2g instead of m1 and m2a on the right-hand side. So we're calling this guy m2. Oh, sorry, and it's a2. So tension upwards minus the force of gravity downwards. Those are the net forces acting on our object, so that equals ma. Newton's second law. Net force equals mass times acceleration. Now, as I just said, the force of tension is the same for both of them. Okay, they have the same force of tension because we're not looking at the pulleys rotating. But we already said A2 is equal to negative A1. So let's put that in over here. In place of A2, let's put in negative A1. So we're going to get negative M2A1. So our unknowns. Force of tension is an unknown. A1 is an unknown. But A1 is the same thing in both equations. Force of tension is the same thing in both equations. So we have two equations with two unknowns. So solve one of them. Say right here we can say force of tension, bringing this to the other side, would be M2G minus M2A, 1. And take this and plug it in for force of tension on this side. So M2G minus M2A1, that's the force of tension, minus M1G is equal to M1A. Oh, A1 still, sorry. Bringing the A1 terms to the same side, we're going to have M2G minus M1G equal to M1A1 plus M2A1. We can factor out the A1. So A1, the acceleration of block number 1, the 5 kilogram one, is equal to M2G minus M1G over M1 plus M2. So M2 is 12 kilograms. I'm going to factor out the G. Minus M1 is 5 kilograms times 9.8 meters per second squared. All over 17 kilograms. M1 plus M2. Comes out to 4.04, so 2 sig figs. Let's leave it at 4.0. 4.0 meters per second squared. That acceleration will stay constant until what happens? One of them hits the ground or one of them hits the pulley, whichever happens first. You notice, if we were treating it as one big object, this is the equation right here that you would have had to come up with. m2g minus m1g would equal the total mass times the acceleration. That's what you would have come up with. Or what you should come up with if you wanted to treat it as a whole. Takes a little practice to get to that point though. So for most people, it's usually better to start with the individual equations for both objects and then make your substitutions.